All right. So earlier I mentioned that if you dropped a magnet into a copper pipe, there would be a current flow in the metal of the copper pipe. What do you think would happen in the case of this astronaut as she orbits around the Earth? Take a quick read. Does anybody have an idea about why what's being described here in this little reflection box, why is this happening? Let's reflect on this together. Does anybody have a thought? Yeah, the magnetic field of the Earth. Look, I gave a lot of help with the picture, right? What we've been saying is that if you take a current loop or something that's a current carrying conductor and you shove a magnetic field into it, you'll induce a current in that conductor. This is just a current carrying conductor. It's a closed circuit. There's not really any load or anything like that. The resistance of the metal itself would be the load in this case, right? And we're not shoving the Earth into the conductor, but the conductor is passing through different magnetic field intensities as the astronaut orbits around the Earth. So if she was going to measure a current flow in her ring, yeah, that would be why. There would be some induced current flow in her wedding ring. Now, do you think that that kind of induced current flow in, not wedding rings necessarily, but in electronics is something that NASA or any, satellite system organization would have to deal with? Yeah.
In fact, some birds they have nerve endings in their eyes.
Yeah.
That function off the same principle, so they can tell the polarity of which way is north, which way is south.
Yeah, that's awesome. I'm so glad you said that. Yeah, some birds do have a little closed circuit. Like it's not electricity, it's not electronic, but they have a closed circuit structure under their eyes, and they use exactly this idea of the wedding ring and induce currents in that closed circuit structure under their eyes to measure what direction is north. And so, if you ever heard that a Canada goose has a compass in its brain, it kind of does, but not a needle compass. It's an electromagnetic compass, and it actually is very much like this wedding ring. I'm so glad you brought that up. You're just like a fountain of knowledge today. Like this is cool stuff, right? So yeah, having an actual compass built into the brain of a bird, that's pretty neat stuff. When it comes to NASA and figuring out if we want to shield our electronics from current induction in our circuitry, 100%. We're going to put little Faraday shields and things like that around our electronics to keep this kind of thing to a minimum, because that's going to cook our electronics. And this kind of magnetic field fluctuation intensifies with solar storms that cause things like aurora borealis, aurora australis, and those solar storms are going to cook our electronics as well. So we want to be able to shield against magnetic field fluctuations in order to not have our telecommunication satellites go down. So what seems like sort of a silly thought experiment with this astronaut's wedding ring becomes about bird navigation, becomes about not having our telecommunications satellites crash whenever there's a solar flare storm. Like this is kind of a big deal, right? Anyway, that's a little brain tickler. Let's go back to this less tickly stuff of shoving norths and souths into solenoids. So I have a professionally rendered diagram of a solenoid with a north getting shoved into it. And I need you guys to take a minute. Look at the way that this thing is being wound. If I shove a north in, what will the polarity of the solenoid be at the top? Right answers only. If I shove a north in, what's going to be the polarity of the top of the solenoid? Everybody together. The answer is 3, 2, 1. One more time. The answer is 3, 2, 1. North. Yeah, everybody says north. All right. So the north is going to oppose an incoming north. On the flip side, if I yank a north out, the polarity of the solenoid is going to be 3, 2, 1. Everybody? South. One more time. One more time. I can't hear you. Oh my gosh. South. Yeah. South opposes an exiting north. Now, if I look at the current, whip out your right hands. Go ahead, whip it out. You're going to have current going away from you on this side. You're going to have current coming towards you on this side. You're going to have current going away from you on this side. Make sure that I'm not lying. If I'm lying, I'm dying. Current's going to go like this. Now, if you follow the labyrinth, that means, is the current going to go Up through this little device or down on the first one? Right answers only. What direction? Look, it's coming out of the page on the left. It comes across the front. It keeps on going. Oh, honey. It's going up through that device. Now, that device is called a galvanometer. Galvanometer, kind of like an ammeter. A galvanometer measures current flow, but it also measures what direction current flows in. So it's measured. It's labeled with a G because it's a galvanometer, but it's measuring the direction of the flow as well. Okay, now modern ammeters will also measure the flow, so people don't talk about galvanometers a whole lot anymore. What would you believe when I yank the current or the magnet back out again? The current flows the opposite direction, and you can check that for yourself. Now, that's just recap, but this is all due to the fact that there's an equal and opposite. How do I finish the sentence? Reaction, yeah. Reaction force caused by current induction, or causes current induction. And I keep referring to this, but this is like the electromagnetic. Take on Newton's third law. I think we could leave Newton behind, but no. Yep.
Would there ever be a scenario where the current flows like away or no?
Well,
It's only going over.
if I shoved a south in, we could have the same conversation, right? Like if I shove a south in, then what opposes an incoming south? A south, and we go through the same logic progression. Okay.
Why is it wanting to oppose it?
I don't know. Why does the sled oppose me trying to pull it? Stupid sled.
It just always.
Well, do the electrons, I mean, on a micro scale, sleds oppose me trying to pull them, and that's where we get tension from, right? On a micro scale, don't you think these electrons don't want to be pushed? And so they resist it. And so I can't, they'll end up moving, but they'll move, they'll oppose me trying to move them. And I think that's like the nicest answer I'm going to give you is that on a micro scale, electrons don't want to be pushed any more than sleds do. And so there's going to be that reaction force. Obviously, there's a deeper answer. That's as deep as I want to go. All right. So when we're inducing AC current, the back and forth motion of a magnet, and I've talked multiple times about pendulums, individual wires, even turbines, but this back and forth motion of a magnet in the vicinity of or within a solenoid will induce a back and forth current flow, and this is known as alternating current. And if you feel like I'm being redundant, it's because I am, because I feel like if we say it enough different ways, it sticks. Do you feel like it's sticking better after a couple days of talking about this? Yeah. That's the point. That's what learning is, right? And sometimes learning is a little bit repetitious, so we get it, okay? If we give this as just a single textbook reading, less people are going to get it. Now, if I take a magnet and I don't shove it in, notice I can't shove it in because there's an iron core in the way. That's a situation of me bringing it close to the solenoid. But would you believe that if I bring this north close, the domains inside of the core are going to actually start to align? Remember, I'm just drawing domains. And wouldn't those domains act kind of like an extension of the magnet? Because we've talked about domain theory before, right? When we talked about permanent magnets, that was actually, by the way, why we had to talk about it, was to be here now where we are. So when I bring this north close, it's like getting those domains to be an extension of the magnet. If I take the north away, don't you think that the domains flip-flop? They actually switch orientations to try and keep that north from getting away. That's interesting. Okay. So I'm going to say that in this soft iron core, domains align and de-align readily. de-align. I don't know if that's, yeah, maybe you don't like that. I don't know. But they align and de-align readily. And we'll even say that domains in the core are induced to align with the magnet. I don't even know. You can put it in writing if you want to, but this is like having an extension of the magnet being shoved right into the solenoid. That is one of the reasons why we use a core. Well, maybe I will put it in writing. This is like, it's like inserting the magnet, but does not require full insertion. Okay? It just approaches the tip of the solenoid. It doesn't actually require to go all the way in. And the reason that you might want to have that, why that would be desirable, is because, hey, you can imagine shoving the magnet all the way in, isn't that going to cause wear and tear? But if I just approach the core, you don't actually have to push it in. There's going to be less rubbing on the actual sides of the solenoid, less breakdown mechanically. Okay, so having this kind of domain core setup, not a bad idea. Pretty clever, actually.